There. Now let's start this over. Okay, so we're going to keep talking about linear momentum, the conservation of linear momentum, and then we will switch over to eventually talking about the conservation of the moments of momentum. And so this is sort of getting into torque and stuff like that. So we'll see if we get it started today. Kind of depends on how quickly we make it through the examples that I've got set up. Announcements. So the extra credit that I announced, today's Thursday, that was on Tuesday. There is an announcement on Canvas. If you have any questions, please let me know. What I've asked you to do is attend for 1 hour and then write up a summary of what you see at the Hydrologic Sciences Symposium next Thursday and Friday. It should be going from 8:30 to about 5 each day, and so that should provide ample opportunity. I don't know. I'm one of the co-directors of that program, and the student committee that's putting it together, I think they have. I'm not sure if they have the final schedule up yet, but if that helps you, it should be up by tomorrow or the weekend. I know they've notified people of when they're giving their presentation, but I'm not sure if they know if they have it posted yet for the rest of us to see. You do need to register. It's free. It's just a Google form to fill out, but I just wanted to let you know that you do need to do that ahead of time to get a Zoom link sent to you to be able to attend. So that's the extra credit. Midterm 2 is on Tuesday. I'll go through the details on that in just a moment. And the final, by the way, has been scheduled. It's on Sunday, May 2nd from 4:30 to 7 p.m. So if you have more than 2 finals on that day, just let me know, send me an email, and we can talk and try to figure that out. Homework is not quite done yet. It will not be due for another 2 weeks, and I figure the thing that's closest to you is probably the next midterm, which is on Tuesday. So I will get that posted by tomorrow. But I just wanted to make you aware that it's not up yet, but it will be. But it's not due next Thursday. It'll be due the following Thursday because we have the midterm coming up next week. Okay, so. Details. So we talked a little bit about this. You can get as many as 5 points. Don't worry about that link. I have a link on the announcement that's on Canvas. You can just click on that one if you want. And the idea here is to just give me 2 paragraphs about what you saw. One is an overview of the presentation. What was it about? Or presentations if they're short, less than an hour. And finally, the second paragraph would be how it relates to class in some way. And that might be as simple as mass balance or energy balance or something like that. But just try to relate it to what we've talked about. And then I haven't set up that location to submit yet, but I'll do that after class today. So April 12th, that'll be due, which is the Monday right after the symposium next Thursday and Friday. And the Canvas announcement is there for you. Okay, so let's talk about the midterm. The scope is chapters 3 and 4, but I've added section 5.1, and the only reason is that was all mass balance where we applied the material derivative and the Reynolds transport theorem to mass. Right. And so because that was kind of the simplest way to do that, section 5.1 is all mass balance. I am including that only because there's kind of a blurry line between chapter 4 and section 5.1. So it's just about mass balance. It's only the application of the Reynolds transport theorem and the material derivative to mass, which, could be simplified to volume or what have you, as we've looked at. So technically, from all of chapter 3, all of chapter 4, remember chapter 3 is Bernoulli equation, so it's the conservation of energy. Chapter 4 is kinematics, and then 5.1 is just applying kinematics to mass. Okay. Same format as last time. The first 10 problems will all be some kind of combination of multiple choice, true, false, fill in the blank, something like that. Those will be worth 2 points each, so that's 20% of the total grade. 5 to 6 short calculation problems. The reason we had 5 last time is because on one of them there were 2 calculations that needed to be made, but these will be short. And what I will do is at the beginning of each one of those, I will put in caps, short calculation, colon, and then the problem. And the reason I'm doing that is because just to give you guys the sense that this is a short problem, not a long one. And so one thing that I hope you will recognize this time when you take the exam is that if you are suddenly writing out an elaborate process of trying to figure out, like the manometry problem last time, right? All you really had to do was focus on 2 points. You don't need to go through the whole thing. You should just be focusing on 2 points or something succinct. Okay, so that's the point of the short calculation problems, is to identify how to just isolate the one thing that's being asked for. So just note if you feel like you're kind of overthinking it or it seems way too big, it might be, you might just need to think about how it gets narrowed down, because that should just be a short calculation. And then the 2 longer problems will be labeled long calculation. I don't know what else to call it, but those 2 problems will have long calculation and then a colon and then the problem statement. One thing will change for these for parts 1 and 2, you will have you'll choose an answer if it's multiple choice or true false, or type in a blank. For 5 through 6, we will do the number entry or letters or whatever, like we did last time. But for part 3, those 2 longer problems, instead of having blanks to fill in, we're just going to have you turn in your work on those. Okay, so what you'll do is you'll write out your answer as you would like on homework or whatever, make a PDF, and then each problem will have its own PDF submission of those last 2. Okay. So in other words, you'll have one PDF for the first long problem, submit that to that submission location, and then the last problem will also have a submission location for just the PDF where you did that work. I'll get back to that in just a second. I've got some more details on the next slide about that. I guess it's actually down at the bottom. The exam will be available starting at 12:30 on Tuesday. The asterisk is for anybody who's abroad, so please get in touch with me and let's figure out what time you're going to take it. Again, we'll do that again. Secondly, this time, instead of giving you 90 minutes, I'm going to give you 105 minutes. And what I want you to do with that, I'm telling you now, and I will put it in the instructions on the quiz tool for the exam, is I would recommend you spend 90 minutes working on the exam, and then you've got 15 minutes to upload your PDFs. And in total, you can submit 3 PDFs. So one will be your work from the 5 to 6 short calculation problems, if you want to submit those. If you're really confident in your answers, we don't have to grade that at all, but you can at least get partial credit if you submit something with respect to the work that's done in those 5 to 6. That's one PDF for those 5 to 6 questions or calculations. Then the other 2 PDFs are the ones that will go with each of the last 2 problems. Okay, I will try to make it very clear where to submit each one of these. They will all be contained in the quiz. They will not be a separate assignment that you need to go find in Canvas and go look up. I think we've got a savvy way of working this out now. So you should only need what's in the quiz as you see it. The reason for this is that I got worried last time when we were like, upload your PDF whenever, is that if you already have the problem written down, you could have used extra time. And so what we're trying to do this time then is limit that extra time that anybody could inadvertently use or purposely use and get beyond the 90-minute limit. So you have 90 minutes, you have 15 minutes to figure out how to make your PDFs and upload them. I just want you to feel comfortable with that process before you start. So if we don't have your PDFs when your 105 minutes is done, we can't give you credit. All right. So unless you run into a catastrophe, in which case you need to reach out to me, we expect to find your work embedded in the quiz, basically on our side when we look through the materials when we're grading. So next slide then, grading. So you must apply appropriate significant figures. So we're going to go ahead and be more stringent about that this time around. We encourage you to carry out units through your calculations But that's not necessary. We're not going to take off if you don't, in the same way that we have done on the homework. I know you're working quickly. You don't necessarily want to take the time to write out all of your units. However, if you get an incorrect answer because you didn't follow your units all the way through, you'll of course lose points, right? You're not going to lose more points because you didn't follow your units through, but we may make a note like if you had followed your units, maybe you wouldn't have gotten this or whatever. So just as a heads up. The work you provide needs to be orderly enough for us to follow your logic and your thought and your process, but we're okay if you are doing something you did it wrong, cross it out and you want to keep moving. That's totally fine. Please don't feel like you need to take the time to erase or whatever. We want you to be efficient with your time, but we also want to be able to review what you've done. So we're not going to hold it quite at the same level of standard as the homework, but we do need to be able to follow your logic and figure out where things may have gone wrong. So there's that. Hopefully that saves you time. Oh, and please, we this time I think we figured out how we're going to hide the grades from you guys until we get all the grading done. But just FYI, please do not worry about whatever number you see by the time you're done, because I think you may only see 70%. Oh no, it'd be less than 70%. You'll see 50% of the exam. We have to do the hand grading. Well, we're going to hand grade 70% of the exam, basically, or 80%, I guess that was what it really comes down to. Everything but those first 10 questions. So you may have gotten some of the 5 to 6 short answer questions right, or short calculation problems correct, which would be fine. But even if you got it wrong, that doesn't mean it was completely wrong. It might just be that you have a typo compared to what I entered as the final number. So please don't worry about that until we get all the grading done. All right, I think, one last little bit of information. So how can you prepare for the exam? And I would recommend a couple of things. Again, I will post the solutions to all homeworks, including the one that's due today, tomorrow at 5 p.m. So those will be available to you. Secondly, I will post some practice problems tomorrow by 5 p.m. as well. So much like we did last time. And then you have, before I move on, I will spend the recitation on Monday going over some of the longer problems that are in those practice problems. Okay, so you can come with questions, we can just have an exchange, but I can also just work out problems that I am posting for tomorrow. And then finally, you've got a number of resources in your e-textbook. And so one of them is, if you're in a chapter, you've got, when you're in a chapter, reading, what the devil? What? Okay. Sorry. Well, this is weird. Oh, there we go. Okay. My pen was disappearing. Okay. So when you're in a chapter on the left-hand side, you can look at the library, I think they call it. It's kind of an index of everything in your book. You can go to these practice and homework problems. And those are ones that are kind of at the end of your chapter, and they have, many of them have answers, and some of those also have solutions worked out. So that can be a resource to you if you are stumped on how to solve a particular type of problem. And then the other thing, so you probably won't see this. This is just my view when I go into the book to begin with. All I've done is press click the link from the main Canvas page on the left-hand side. I think it says Wiley Resources, and I end up in a new page, a new browser page that looks like this. If you click on practice, you'll have another set of problems to work with. And I guess I haven't compared them perfectly, but I'm pretty sure that they are different than these ones. So these are kind of two different resources for you to use and get some practice with. Okay? All right. With that, I'll stop talking and take any questions if you have any. All right. Is Emma or Alexi, anything coming through the chat?
No, there's nothing in the chat.
Okay, terrific. All righty. Okay, well, if something comes up, send me an email. We will plan to have all of these ready by 5 p.m. tomorrow. That's Mountain Daylight Time. If there is some problem with that, I will send an email and let you know if there's some delay for some reason. But otherwise, I'll plan to have those queued up so that they become available at 5 p.m. So you should be good to go. All right. Terrific. Okay. So on Tuesday, we talked a bit about this conservation of linear momentum. And we said, we wrote this long equation. It looks a bit like the ones we've talked about before, particularly with respect to mass flux, except that we have a new velocity term that's included now. And what's really important is that velocity term is a vector and has direction to it. So we do need to pay attention to which direction this new velocity vector that's inserted, basically here, here, and here, and here, which direction those are going, because it will change the sign, the SIGN, of each one of these terms potentially, right? Depending on how we've set up our sign convention for the particular problem. So we said that the rate of change of the system momentum is equal to the rate of change of momentum in the control volume plus the net flow of linear momentum across the control surface. So again, we're looking at, remember we have a plus for the outflows and a minus for the inflows. And the reason for that we talked about is because when we go back to the integral component of this, we have that n hat vector, and that unit vector is always normal to our control surface. So it's always pointing away from the control surface, right? So the inflows will have a negative value to them simply because that normal unit vector is in the opposite direction of the inflowing material, or whether it's mass or heat or whatever we're tracking in the problem, in this case, linear momentum, that those are going in opposite directions. And then on the plus side, we have the outflows, which are going with the normal unit vector. So those are in agreement with the direction out of the control volume and away from the control surface, okay? Now, the first thing I have queued up here are a set of recommendations, like kind of rules to help remind us kind of how to work through these types of problems. There are 9 of them listed in your book. I've pulled 7 of them because the other 2 I thought were they were just a little more detailed than I thought we really needed. But the main 7 I pulled together here and tried to make them a little more succinct. So we'll go through those next. I did forget, I guess, that I had this one more slide from Tuesday where we had said that let me get the words right. The rate of change of the system momentum is equal to the change in the external forces acting on our control volume. And so we can replace the left-hand side now with the sum of forces, these external forces. The internal part of it, or the right-hand side of this, remains the same. And the first term, whenever we have steady flow, will be 0. Right? We have steady movement, so there's no change in the internal linear momentum with time, but we may have differences in inflows and outflows, right? And that would manifest themselves in some of the external forces that would not be 0, for example. So for steady flow, this is what we end up with. So by basically getting rid of this first term on the right-hand side. And then if it's also incompressible flow, then we can just turn this into rho times q times our velocity vector, sum all of the outputs, subtract the sum of all of the input linear momentum flows as well on the right-hand side. So these are just kind of shorthand ways of getting at these external forces acting on our control volume. All right? Okay, so some generalities, rules, whatever, guidance, whatever you want to call this. So the first one is when flow is uniformly distributed, over a section, of the control surface where flow into or out of the, not controls volume, but control volume occurs, the integral operations are simplified, right? What that means is that in this case, you could imagine that a particle here, a particle here, a particle here, they're all going at different velocity vector values, right? And so this becomes more challenging to deal with some sort of a distribution of velocity than this over here, where all of these particles are going the same velocity, and our velocity vector then is uniform across the cross section. So, as it turns out, one-dimensional flows are easier to work with than non-uniform velocity distributions. And that's generally true when any kind of problem we're working on. But with linear momentum in particular, it's quite helpful so that we can have a single velocity vector that is representing the linear momentum at an inflow or an outflow location. Okay. It's interesting. We're actually given no information about this one. This was an example we looked at on Tuesday. There's actually no information about that one, or maybe this was from last week. But in any event, there was no information about that. So we assume that we have uniform velocity across that cross section, leaving that location. Okay, so there's the first generality. The second one is that linear momentum is directional. It can have components in all three orthogonal coordinate directions. It can also be positive or negative depending on the particle's direction of travel. Oops. Oops. Dang it. So recall this nozzle problem that we worked on, example 2 on Tuesday. You know, one of the things that we talked about, we had all of the flow was vertical, right? All of the velocities. So we have a W1 here. It's not shown here, but we had a W2 down here. 2, right? Remember, those are going in the negative x direction. So all velocity was heading in the same direction, and I'm sorry, negative x, negative z, the negative z direction. So positive z is indicated to be upward. So any downward move velocity is going in the negative z direction. So both W1 and W2, they have different magnitudes, but they were going in the same direction, and they were both negative if we were summing or assessing momentum, linear momentum in the z direction. So all linear momentum was in the z direction, and because it was downward, so both W1 and W2, all linear momentum was treated as negative. Okay, now I'm saying that without including without putting it into the equation where we have to assess an inflow and an outflow of the control volume, right? This is just the direction of the linear momentum at the moment at this particular junction. Okay. Number 3, so this is where the next sort of complication comes in, is that the flow of linear momentum into a control volume involves a negative v dot n hat dA. Okay, that term, remember that this is what we're integrating in that second term on the right-hand side of the Reynolds transport theorem that includes linear momentum. This piece right here, I guess we could go all the way to dA, but this piece is will have a direction for v and a direction for n, right, for our n hat. So the flow of linear momentum into a control volume involves a negative v dot n hat dA, and the flow out of a control volume involves a positive v dot n hat dA. Okay, and then we've got the velocity vector outside of that in its direction. So note that there are two signs to keep track of: the direction of velocity, the velocity vector, positive or negative, and then whether the momentum is into, which is negative, or out of, which is positive, the control volume. Okay, and we'll go through a couple of at least one or two examples of that coming slides. Okay, so let's look at these four different cases right here. We have an inflow here, and of course our n hat is out, and then we have an outflow here of the control volume. So on this upper end, n hat dA is going to be, this whole thing is going to be positive here, right? This is negative, but it's an, it's an inflow, so it's negative, but the V is going in the downward direction. So as long as we think about Y as being positive upward, two negatives multiplied together give us a positive here, okay? On the other hand, on this other side, you can see that we have now velocity going in the positive y direction, and because this is an outflow, it will be positive as well. So this ends up also being positive, okay? For the same rules, the same reason, but you know, the reverse of each of those rules in this case, because it's an outflow and it happens to be going upward in the y direction. Okay, so what about these two down here? Now we have an outflow V is going downward in the y direction, so that would be negative. Because it's an outflow and we're going with n hat, we would have a negative value down here, right? And then over on the right-hand side, this lower right-hand corner, now we have velocity going in a positive direction. And because that's an inflow, we know that should be negative, right? So we have a positive velocity, or a velocity going in the positive y direction, but because it's an inflow to the system, to the control volume, this is also negative as well. A negative times a positive gives us a negative. Okay? It's funny, when I was working on these notes, I actually had these sort of not reversed in my mind, but the two right ones were reversed in my mind, and I was like, oh, the book is wrong, and I was like, how could they make that mistake? And as I've thought through it, I'm like, oh no, that's right. Now I get it. Okay. So again, you can work through these. There's a slightly different explanation in the book, which is a little bit longer. I've been trying to make these a little bit more succinct. Okay, number 4, the time rate of change of the linear momentum of the contents of a non-deforming control volume is 0 for steady flow. So in other words, the first term on the right-hand side of our Reynolds transport equation is del T. It's supposed to be a del over the control of the integral over the control volume of V rho. Come on, rho dV. Now this one is volume. Okay, so there are two ways to look at this. We can say that the rate of change of this linear momentum of the contents of our control volume is 0 when we have steady flow. Now that steady flow could mean two things. The first, of course, is that I'm going to write it as del V del T is equal to 0. Again, because it's steady flow, it's not changing in time. So del V del T is equal to 0. I would also argue that the other thing that occurs here is that del rho del T we expect is also equal to 0 if we have steady flow. So we can kind of think of it as like steady mass flow. But assuming that, for example, we're only putting water through a system and that all the water is going to have the same density, then we can just focus on the steady flow part of this, that is the velocity component being with no change in time. So del V del T being equal to 0. And most, if not all, problems that you work in this class will be steady flow. The one exception was, I guess it was steady flow, but you were still accumulating water, was that reservoir problem you had in today's, the homework that was due today. That one did have a change in storage because it wasn't a fixed, non-deforming control volume, right? As a reservoir, it can rise and fall its level, and so it could store water if that's our control volume, is the reservoir itself. Okay, so that's number 4. Number 5, if the control surface is selected so that it is perpendicular to the flow where fluid enters or leaves the control volume, the surface force exerted at those locations by the fluid outside of the control volume on the fluid inside the control volume will be due to pressure. So in other words, we have to consider pressure force that of course is equal to P times some cross-sectional area, right? Where that pressure occurs. So P out, A out is a force that's acting on this edge of this particular control volume, and P in, A in is a force acting on this control volume at the inflow. Okay, so we can't forget our hydrostatics essentially. So somebody asked about whether we were going to have hydrostatics covered in the midterm 2. Not really, but sometimes the concepts come through, right? We can't ignore them completely. Okay, number 6, the external forces have an algebra.
Professor, do you mind going back just for a little bit?
That one?
Yeah.
Okay, sure. So in this case, all the flow is upward. It's coming from the bottom, going up out the top. P out, A out might be 0 if this was a free jet of some sort. But we don't have any information about that. So assuming that there's some column of fluid above the outflow, and often, as you saw in the homework, you would get a pressure value that would be given at the inflow and outflow. So those are useful to us to make these particular calculations, to get these forces. All right, am I okay to go on?
Yeah, thank you.
No problem. Okay. Number 6, the external forces have an algebraic sign. Positive if the force is in the assigned positive coordinate direction, and negative otherwise. So what I'm going to do here is just draw that, if this is sort of an XZ system, right, in two directions, 2 dimensions, then, we could imagine an FAZ component and an FAX component to this particular force. Similarly with E, we could, FE here, we'd have some Z component and some X component. And you can see the way I'm drawing these, they all have some direction to them. So FCX and an FCZ, right? So we could draw that for any of these. And essentially then what's important is when we assess the external forces summing together, we have to get the right directions on these to get the right sign on them, right? To know whether they're positive or negative in their directions. Okay, that's number 6. So I've got one more, and then we'll go through the U-turn 180-degree example together. All right. So number 7 is that the force required to anchor an object is a function of generally 3 things. 1, the surface pressure and shear forces acting on the control surface. 2, the change in linear momentum through the control volume. And 3, the weight of the object and the fluid contained in the control volume. So when we went through this example that we have on the right-hand side here on Tuesday, remember that this component, or these two components, so there was the weight of the water, I think I gave that wings, and I think we called it WN, the weight of the nozzle. Those two were really small. Right? It was important to still calculate them because they were vertical forces that were included in the system, but they just happened to be quite small in the overall scheme of things. I think the pressure forces might have been the biggest, and then the linear momentum was next. But those were much larger in both cases than the two weights that came out of this. So just a heads up. Again, you can't discount them completely, but from a magnitude perspective, they tend to be fairly small. Now, that was for that particular example. Of course, we could have other types of examples that where those would be much more appreciable potentially. Okay, so the next example that I have queued up is one that is similar to the homework that you guys worked, one of the Wiley problems that you worked on for today. But I wanted to go through it a little bit. I don't think it's identical. And just talk through putting together all 7 of these generalities in a particular problem, okay? Give you guys just a couple more seconds to get that down all the way. But again, this is there are actually 9 in your book. So bonus, 2 more generalities in your book if you go to that. Okay. Example 3. So water flows through a horizontal 180-degree pipe bend as shown. The cross-sectional area is constant at 1 square foot. Through the bend, the magnitude of flow velocity everywhere in the bend is 50 feet per second. The absolute pressures at the entrance and exit of the bend are 30 psi and 24. So P1, this is P1, and this is P2. Calculate the horizontal components of the anchoring force required to hold the bend in place. All right. So on the left-hand side, well, the far left, we have a PVC 180-degree bend. I think that's probably a 3 or 4 inch diameter piece. Actually, it's two. Oh, that's actually maybe it's two elbows put together. But in any event, you get the idea that we can have these bends that would cause a 180-degree change in direction. All right. The velocities remain the same all the way through the inflow and outflow, and we have a consistent cross-sectional area. So, you might be tempted to just say, well, so the linear momentum is going one direction and then the exact same magnitude is going the opposite direction. Who cares? What does that matter? Well, let's put this together and demonstrate how the force that comes out of assessing these linear momentum conservation will give us an important value to have to deal with. Now, on the right-hand side, I'm showing the forces. So this is kind of my free body diagram now. I've got my pressure force on the upstream end and the pressure force on the downstream end. Those are both in the positive y direction, okay? And then I have my velocities going in 2 opposite directions too. Little v1 is the entrance velocity, and it's the y component, right? I have no x and no z. So whatever velocity I'm given, this 50 feet per second, is my little v1. And then little v2 down here is the same magnitude, but going in the opposite direction. So if I were to write these out, little v1 would be positive and little v2 in the y direction would be negative, all right? If we're gonna put those into a directional context. Okay, the other thing I didn't mention is that now we have these forces. These 3 forces. So we have the weight of this thing acting in the downward, the z direction. We have potentially some FAX and some FAY. The FAs, FA, X, Y, and Z are, the A stands for anchoring. So this is an anchoring force, and it can have three components, right? It can have a force in the Z, a force in the X, and a force in the Y. In this case, we are given no information about anything happening in the X direction. So we can expect that this anchoring force is going to be zero, right, in the X direction. I'm going to leave out the Z direction for the weight part of this, but only because we don't have the entire volume of this bend to be able to calculate the weight of the water, nor do we have information about the weight of the pipe material itself. Okay, so let's just focus on the horizontal at this point. So essentially, what is FAY? Now, you'll see that we transfer from what seems like a simple force setup. And by the way, it is the way that FAY is drawn is just in the plus Y direction. That's just sort of a gimme for, we need to draw it in some direction. The reality is it's probably going in the opposite direction, right? You can imagine that water moving at 50 feet per second, which is really fast, hitting a bend and going around is probably going to have a net force, or the linear momentum is going to kind of push us more to the right than to the left, right? Then anchoring force doesn't need to keep it from moving to the right. It needs from to the left. It needs to keep it from moving to the right. All right. So now let's take this one step further. Now we see these R's. Here's an RZ, an RY, and an RX. R is the force that the bend exerts on the fluid inside of it. Okay, so we're just going to focus on the anchoring forces, but note that you could also calculate these reaction forces as well inside of the pipe. And then finally, on the lower right here, if we just look at these in the Y direction, if you were going to solve for RY, you would basically have RY, you would expect acting in the left direction. FAY is probably also going to be acting in the left direction, and then your atmospheric pressure component would have a role here too. But for now, let's not worry about all this stuff. Let's just focus on figuring out this FAY component. Okay. So for the sake of completeness, I am going to show the X direction here real quick. The sum of the forces in the X direction are equal to, in this case, just FAX is the only force acting in the X direction, and that is going to be equal to this integral over the control surface of our linear momentum. So U times rho, oh goodness sakes, times V dot n hat dA, and we note U1 is equal to 0, and U2, the outflow, is also equal to 0. So ultimately we can say that FAX, so I could take the time to write out sort of an m dot times V on the right-hand side and break this into the inflow and outflow. I'm going to skip that and just note that because the U's are equal to 0, there's no velocity in the X direction, that FAX is equal to 0 as well. Okay, so that's the sort of complete aspect of just sort of dealing with this particular problem. And by the way, now I can't remember exactly what number it is, but this is a fully worked out example in your ebook as well, your e-textbook. Okay, this gets more complicated for the Y direction. So let's take a look at the linear momentum change that's occurring in the Y direction and how that influences the FAY, the force that's holding, the anchoring force that's holding this bend in place in the Y direction. Okay. So similarly, we can start with the sum of the forces in the Y direction are equal to basically FAY, and I'm going to go ahead and leave it. Oh, I copied the wrong one here. Anyway, real quick, let me just show you. I meant to keep this one, but FAY, because it's been drawn in the positive Y direction, I'm going to keep it that way, right? I mean, if I had drawn this myself, I probably would have drawn it negative and then put the negative sign in front. But if we end up with a negative, we'll know it's going in the opposite direction. So FAY, and then this is equal to then our change in linear momentum. So the integral over the control surface of the flow of linear momentum, V times rho times V, V dot n hat dA. Okay, and so we can now break this integral into two pieces. We are going to look at the inflow of the linear momentum and the outflow. So the left-hand side is, I actually forgot two forces. I forgot about my pressure forces. Let me do this. Sorry about this. I'm going to add these on to the end instead. So this is incorrect to just say it's FAY. It's FAY acting in the positive Y direction, and then a plus P1A1 and a plus P2A2. Okay, so you might be wondering, why are both of those positive? And the reason they're positive is that the control volume that we've drawn has a face on this side and this side, right? So those are vertical faces, and the pressure is always acting normal to our control surface. And so in this case, they're both acting in the positive Y direction. So that's why they're drawn this way in the positive Y direction in both cases. Okay, so those are our pressure forces we have to account for as well. All right, so now let's rewrite this then. So this should be AY. So FAY plus P2A2 plus P1A1 is equal to, now we've got, remember that we're just gonna, when we go to linear momentum, we're basically multiplying a velocity that's occurring in the Y direction, at both the inflow and outflow, by an m dot, a mass flow, right? A mass flow rate. So we're going to have, on the inflow side, we will have a plus V1 and a minus m dot 1. So why is that negative? Because we said that the inflows, so basically the V times n hat dA, that the inflows are negative, okay? So that's where the negative comes from for the mass flow rate. The velocity is acting in the positive Y direction, so it has a plus sign, right? And then we're going to add what happens on the outflow, the outflow as well. So the outflow has V2 acting in the negative direction, right? And it has a plus m dot 2 occurring there as well. In other words, remember the outflow is a positive V V times n hat dA. All right, so that's where the positive comes from on M2. The velocity V2 is acting in the negative Y direction, so it gets a negative in front of it. All right. Now let's take a moment to say that we expect, of course, that rho 1 equals rho 2, and of course we know that with no change in cross-sectional area and no change in velocity, we expect that Q1 is also equal to Q2, and therefore we would expect that the mass flow at 1 is equal to the mass flow at 2, okay? And therefore let's just rename it the mass flow rate instead of designating 1 and 2. All right. And when we calculate this, though, we could use either the inflow or the outflow. So it does have a quantity to it. It will be 50 feet per second times another 50 feet per second times the density times cross-sectional area, something like that. Sorry, that was the momentum. The mass flow rate is only the density times the velocity times cross-sectional area. So it would be like, what are we working in feet here? I can't remember. Yeah, so it'd be like 1.94 slugs per cubic foot. So let's just maybe go ahead and do that. So we've got the value already. M dot is equal to rho, and then I'm just going to use A1 and V1, but you could have used A2 and V2. Remember, they're all the same values anyway. So in this case, then this is equal to 1.94 slugs per foot cubed times, and then our area is 0.1 square foot. And then finally, the velocity we have is 50 feet per second. When you multiply all of that out, you get 9.70 slugs per second. Okay, so now we have M dot, and we can plug it into this equation, and we know those velocities, we know the pressures in the area. So essentially, we should be able to solve for FAY now. Okay, so let's do that on the next slide, but I'll give you guys a second to catch up. Make sure you get all this written down.
Hi, could you go over again when looking at momentum, how to decide the sign of momentum based on like the direction of the arrow and if it's going in and out?
Yeah,
Just
so
go in, or why
the M dots are the way they are?
Yeah, just like those two
Okay.
ways that you can change the sign of momentum.
So the master fundamental equation tells us that outflows have a positive sign to them and inflows have a negative sign to them. Okay. So when I put that positive and negative in front of the M dot in the problem we're working on now, that's where these signs are assigned to those M dots based on whether it's an inflow or an outflow. So outflows are positive, inflows are negative. All right. So that was part of this generality as well, number 3 here. Okay, that you have inflow and outflow gives you plus or minus just for which direction you're going for the M dot, but then the velocity will also have its own direction to it, right? So in this case, keep going here. Okay, so in this case, M dot 1 got a negative because that's an inflow, and then it got a positive on the outflow end. M dot 2 is positive because that's an outflow. Okay, so that comes from the Reynolds transport theorem. Then these velocities are either going in the positive or negative direction. So V1 is acting in the positive y direction, and so it is plus, and V2 is going in the negative y direction, so it gets a negative. Okay? Hope that helps. All right. So on the next slide, now we're going to just go ahead and put all the numbers in for this equation right here to calculate this anchor force, the y direction component of the anchor force. So now FAY is equal to, hang on real quick. Did I drop that negative? Oh, I know. Yeah, okay. Sorry. Maybe I need to take one more step. Yeah, let's do this. Okay, so let's rearrange that equation so that we isolate FAY on the left-hand side. So if I do that, I have FAY is equal to minus M dot times V1 plus little v2 minus P1A1 minus P2A2, and then I think that's it. So all we did was rearrange the equation on the previous slide algebraically. Now we can plug and chug through to get our numbers. So this would be equal to a negative 9.70 slugs per second, and then multiplied by this sum of the two V's. Now it turns out they're both the same value, so I'm just going to have 50 feet per second plus 50 feet per second. And then I subtract P1A1. So this would be 30 pounds per square inch. So I need to convert that to square feet, pounds per square feet. So I'll multiply by 144 inches squared. Oops, I forgot my square. Inches squared per foot squared. And then I multiply by the area, which is 0.1 square feet. Okay. Then I have to subtract P2A2, which is now, instead of 30 PSI, we have 24 pounds per inch squared times 144. Oops. Once again, this conversion, 144 square inches per foot squared, and then multiplied by our area again, same number, 0.1 feet squared. Okay, so when we work all this out, we end up with FAY being a value of minus 1,748 pounds of force. So one thing about that, before I take this a step further, one thing about that is that because it came out to be negative, what that means is that FAY is actually acting in the opposite direction from the way that we wrote it in our equation, okay? The second thing about that, of course, that some of you are probably stuck on at the moment is like, we're not paying attention to sig figs. And the smallest significant figures we had was 1. So this should come out to like minus 2,000 pounds or something like that with respect to if we account for significant figures. Okay, any other questions on that?
Someone has a question in the chat. Let me just, since we are given pressure in PSI, do we need to adjust it somehow? Usually we work with gauge pressures.
Oh, PSI-A, right. The A was absolute. Yeah, good question. In this case, you don't have to. It's a closed system, and we're not somehow interacting with the atmosphere. So all we really care about is ultimately this comes down to a pressure change from one point to the next. So you can work with the absolute that's given, but that is a great question. If we had put these in gauge, they would be big time negative, I guess, right? Because they'd end up being really small pressure value or very negative. Large negative values is actually what they'd be. So yeah, good question. Thanks for asking that. Okay, terrific. All right, we're going to do something a little bit different on this one. I want to, let me walk you guys through it, but then I want to break you guys into groups and just have you work on one piece of this, only one piece. And then we'll work the whole thing together. So here is a sluice gate on the right-hand side. You can see two versions of it. One is when it's closed and there's no water coming out. And then when it opens up a little bit, it's got water coming out of it, obviously. So we're given some dimensions on the left-hand side here. The width of this thing into the screen or out of the screen is 1 foot. Okay, so we're going to start with this and just consider what we call unit width. So per unit width, what is the force that we need to keep the sluice gate in place, right? U1 is going to be a velocity when the sluice gate is open. On the left-hand side, this would be U1 coming in. And it's an inlet velocity of 4 feet per second when the gate is open. And U2 down here is going to be some sort of exit velocity, right? And you can see that H, the total height, this isn't quite drawn to scale because H, big H, capital H, is 6 feet of water behind the sluice gate. And the sluice gate opens, when it's open, we have a little h equal to 4 feet. So that looks more like 4 inches compared to 6 feet. But anyway, you can imagine it opening to about 2/3 of the height here. And then Rx is a horizontal anchor force that's indicated. So Rx, you can see when the sluice gate is closed, we have Rx acting here, and then we have some other force acting on the left-hand side. When it's open, we have this other set of forces. All right, so the question is, or determine the magnitude of the horizontal component of the anchoring force per unit width required to hold in place the sluice gate shown in the figure. Compare the results with the size of the horizontal component of the anchoring force required to hold the sluice gate in place when it is closed, and the depth of water upstream is 6 feet. Neglect any friction forces. So essentially, we're being asked for 2 cases. Case number 1 is when it's, I can't write anymore. Case number 1 is closed. When the sluice gate is closed, what is Rx? And then case number 2 is when it's open. What do we do? Okay. All right. So what I want to do is put you guys into groups for random groups for 5 minutes and let you work on the closed case, and then we'll solve that together, and we'll solve the open one together. Okay. So let me see. We have 77. So 5. So about, let's try 25. Where are my? Wait a minute. Participants. Hey, what happened here? Thought I could put everybody. Oh, maybe can I not do it? Breakout rooms. All right, there it is. All right, so we're going to go with 20. Let's do 20 breakout rooms. I'll let you guys sign automatically and just spend 5 minutes working the closed problem, and then we'll come back and check your answers. All right, here we go. Oh yeah, I should mention maybe somebody take a screenshot. Shoot. Sorry. Before you go in your group. So Emma, it looks like you're not working from your phone anymore.
Yeah, I've upgraded. I'm now on an iPad.
Oh, okay. Yeah.
Soon I'll be back on the computer. And I won't be
bigger.
looking down on one.
But slightly
Yeah.
bigger surface.
Yes.
Are you still in Arizona?
No, I'm back home.
Oh.
I just have to get all stuff. My computer's struggling a little.
Let's just see here. Is there anybody in a room by themselves? See a room of 2. That's it. Okay. Oh. 2, 2, 2, 3, 3, 3. Huh. Okay. Well, yeah, looks like it's all together there. Okay. So this is working out well today. So let's see. If we finish this one. Oh, and then I've got my my reef questions. That's a good break, and we'll start moment of momentum after the exam next week. So this actually works out pretty well.
So this most recent homework, that material isn't going to be on the test, correct? Right?
Half of it will, just the
Okay.
math balance part. That I want to say it's the first 4 problems of Wiley and the first of the 2 written problems.
Should we try to grade the homework like faster? I guess because I know like if they want to use it to study, I don't know. Like,
Well, they'll have the solutions though.
oh, they'll have. Oh, yeah, you're right. Yeah, I didn't think of that.
Yeah.
So I guess no. I mean, no rush.
Don't have to.
Yeah, you're good to get it done soon.
Yeah, yeah, because as of Tuesday, we'll have the exam to grade then too.
Yeah. Emma, I just had, like in your research group, there's a giant Google Docs that I was invited to like many, many years ago when I was doing the undergraduate research, and I'm still in it. I just realized recently. So like, I'm like, to me, I'm more just nervous that like one day I'll accidentally delete something from it or something like that. Like, I don't want to be part of this like giant Google Doc with all this.
You don't want that pressure, man.
Yeah, I don't want this like.
Our drive, like our entire drive that you're in,
Yeah, like the
with all the folders and everything.
Yeah,
That's
yeah, I
funny.
have access to that. So I don't know if you should tell Amy to like kick out all the old DLA students from years past. So like someone
It's probably kind of fun to like snoop or something. You can see
how
what
things have
happened.
changed.
Yeah. See what happened to the person you were working with. Who did you work with? I don't.
I was
think
with
know them.
Nick and Kimmy.
Yeah. I don't know.
Yeah. Okay.
Oh, Kimmy, I know.
Yeah, I think Nick graduated a few years ago. Yeah, I just thought
Yeah,
it
go
was
see what Kimmy's up to.
it's like research team SWS, like just the giant file. Like
That's funny.
I'm sure it's backed up somewhere, but I don't know. It just feels like this should be not.
Yeah.
All right, I'm gonna give them all a minute to come back here.
Are you excited for your
Interesting.
presentation?
What's that?
I asked if he was excited for his
Oh, yeah.
presentation.
I think so. Yeah. Won't be that long, only 15 minutes.
Oh yeah. So Alexi, did you
Yeah.
figure out what time?
I don't think they've emailed me with what time yet.
Okay.
But I just know it'll be like on Friday because I said I was free all of Friday. So
Okay. Cool. Yeah, we ran into a funny problem. Devin, I don't know if you know her. She's I think a PhD student over in ATOC. She emailed me and was like, "Hey, I see you're working on the schedule. I got my vaccine appointment." And so I emailed the group, who's coordinating. I'm like, "Hey, can you guys accommodate this?" And they're like, "We don't have her abstract." I'm like, "Oh no." Had a few of them like that. All right, 10 more seconds for folks to come back. 4, 3, 2, 1. Okay, everybody's back. All right, so does somebody want to volunteer a number that they got? What magnitude of RX did you get for the closed sluice gate? Anyone come up with a number? Now, the closed sluice gate is basically the condition, the example that we had from 4 weeks ago or whatever, right? Or 8 weeks ago. This was basic hydrostatics. So when the sluice gate is closed, we essentially end up with, contents of the, okay, so this guy ends up going to 0. There's no change in time. And as it turns out, there's no linear momentum. There's no velocity occurring anywhere for the closed gate condition. So we have to note that the sum of the forces in the x direction equal to 0. So we end up with going back to fluid statics. So we would have, our hydrostatic pressure acting on this side, and then some reaction force holding that in place. Okay. Now, we're not going to worry about its location. We're only going to worry about its magnitude at the moment. So we would say, oh, goodness sakes, that was supposed to be a gamma. So the hydrostatic force on the left-hand side is gamma water, right? The specific weight of water times its acting, or the value of it. We multiply by h/2 to get to the middle. Then we multiply by the area of the sluice gate, and we were given a width of B, right? It's acting over all of H and B wide. And then the other force acting here is just Rx acting in the opposite direction. So this is Rx, and the other is our hydrostatic force. These are going to equal 0. So we can solve for Rx. Oh, gosh. Rx being equal to 62.4 pounds per cubic foot. And then we multiply by, I'm just going to put this in, H is 6 feet. So 6 feet over 2 obviously gives us 3 feet. We multiply by H because we need the area still. And I'm just going to put 6 feet squared because B is 1. So when I multiply capital H by B, I just get 6 square feet. And so when we do this math, Rx comes out to be 1,123 pounds. Okay? So this is basically our force balance here that is acting in the X direction. Okay, so that makes sense. We kind of went back to basics. Now what happens when the gate is open? We're still going to have a force, the hydrostatic force acting on the top part of the gate that is still, in contact with the water. But we also have to account for the linear momentum change through the system, okay, or through our control volume rather. So in this case now, we're going to have, no change in what's stored, but we will have to deal with this component. And then on the right-hand side, we'll also have hydrostatic force included here. So now we're going to, let's see, I want to do this in the right direction here. Okay, for the gate open case, am I missing something? Okay, all right, this feels a little bit odd. Okay, there it is. Okay, so let's just work the sum of the forces. We're going to have to include hydrostatics and stuff. Let's leave that alone for a second and just work with the linear momentum part on the right-hand side real quick. So these are these external forces. We're going to leave that alone. And on the right-hand side, when we're just dealing with this integral piece, we're going to deal with the incoming linear momentum. So when it's coming in to our control volume, remember that it is a minus m dot 1. But the u, the velocity, is acting in the positive x direction, right? So there's x being positive. So this is a u1 times a minus m1. And then we're going to add to that what happens at the outflow. And in this case, the outflow is also in the positive x direction. So u2 times, and then because it's an outflow, it's positive, our mass flux is positive, m dot 2, okay? So now we need to figure out what U2, we're given U1, what is U2 and what is m dot? So this can boil down to, we note that M1, during this condition, m dot 1 is equal to m dot 2. We're not given any information about a rise or fall or anything. So any of the water coming in on the left-hand side has to be coming out on the right-hand side. So we're just going to call that m dot. And we can now rewrite this upper equation to just be m dot times U2 minus U1. Okay, so all I did was transfer that negative term and then group these. Also, we note that Q1 is equal to Q2. So the flow rates are going to be identical here as well. And when that occurs, then we can say that U1A1, that's the flow rate into 1 on the left-hand side, is equal to U2A2, the flow out on the right-hand side. So this is let's just solve for U2 first. So U2 is equal to U1A1 over A2, right? And that's equal to 4 feet per second. Feet per second times A1 is H times 1, big H times 1, so that's 6 square feet. So I'm just going to save us, 6 feet squared divided by A2, which is 4 feet squared. So it's little h, 4 feet tall and 1 foot wide. So I'm just doing that multiplication to save us from me scribbling out a 1. So when we do this math real quick, we just get 6 feet per second, okay, for U2. So now we can plug into this equation to figure out what the right-hand side is. And now it's time. I suppose we could do that. The sum of the forces externally here is from the momentum side are equal to m dot. Oh, I guess I have this done a little bit differently. On the right-hand side, the rest of these external forces equal. I'm going to come up with this piece of the pressure force by doing this by difference. So I know this is going to seem a little bit silly, but I think it's going to work out. So we would say gamma W times H over 2, big H over 2, times H times B minus the component that would just cover the lower section, gamma W times little h over 2 times little h times b, and then minus Rx working in the opposite direction. So it's not that this force has a negative direction to it, it's that we're subtracting it from the entire h that comes down. Now, we do actually know little h and big H, but I just figured this was an okay approach to use to put these together. Oh, I didn't realize we're past time. Okay, so let me wrap this up, and then we'll work on the. I just have the clicker questions right after this. Okay, so the last thing here then is gamma W times big H over 2 times H times B minus gamma W times little h over 2 times the cross-sectional area H times B minus Rx is equal to m dot times U2 minus U1. And we can solve all of this for, I'm going to take 2 steps here. Rx moving to the left-hand side and then substituting in all these values. We end up with 62.4 pounds per cubic foot times 3 feet, which is big H over 2, times the area of big H, 6 feet squared, and then minus 62.4. Oh, what did I do? 624. 62.4 pounds per foot cubed times, now we have 2 feet, little h over 2 times 4 square feet. And then we subtract this m dot is going to be 1.94 slugs per cubic foot. And then we multiply by, I'm just going to work on the upstream end here. So it's rho times A times V. So V is 4 feet per second, and A is 6 feet squared. And then we multiply all of that by this difference in U's, 6 feet per second minus 4 feet per second. Right? And when we work all this out, Rx comes out to 531 pounds per foot of width, or per unit width, either way. Goodness sakes. Okay, 500, and that should be a 3. Sure doesn't look like it, Wacom. All right. So 531. All right. So the last thing I have, I'll give you guys just a second to catch up, is the 2 quick clicker questions, and then I'll stick around if anybody has any questions. Okay. So the 2 questions come back to linear momentum, and they look like this. two fluid jets are pointed at surfaces as shown in the figures below. The fluids are incompressible and the effects of gravity can be neglected. The mass flow rate and the velocity of the jets are identical. The cross-section area of the jets does not change significantly as the fluid flows. So the question here is, how is F1 related to F2? So in F1, we have a horizontal F1 force acting in the left-hand direction. The fluid stream gets deflected up. In the case of F2, it is being curved back around. So is F1 equal to 2F2? Is F1 greater than 0 and F2 equal to 0? Is F1 equal to F2 over 2? Is F1 equal to 0 and F2 greater than 0? Or is F1 equal to F2? All right, we're at 45 seconds. One hint I'll give you, F1 and F2 are acting in the horizontal direction. How many folks do we have left? Okay, so we've lost a few here. Okay, we're up to 61. All right, let's take a look. Okay, interesting distribution. So the most was C, F1 is equal to F2 over 2, and it turns out that is the correct answer. And the reason for that is that in F2, you've got the linear momentum working all in the X direction. If we were to draw a control volume that looked like that, in the top one, you can see that it's deflecting. So this is acting in the X direction. This is now in the Z direction. F1 doesn't care about what happens in Z, only in this horizontal direction. So that's why this ends up being the right answer, is simply that we know we have half the linear momentum that occurs here gets shifted in the top one at F1 to go up into a totally different direction. So it's not accounted for. Whereas in the F2 case, it is acting, both of those are acting in the horizontal direction. And so regardless of what those numbers are, that's how they're related to each other with nothing else applied. Okay, sorry to go so long. I'll let you guys go, and I'll have a great weekend. I'll look forward to seeing you on Monday at recitation, and Alexi will have his normal office hours on Monday morning as well. So I'll stick around if anybody has any questions, but otherwise, take care.
Thank you.
Thank you. Let's see. Shoot.
Thank you.
You bet. Take care.
Professor?
Yeah.
I was about to answer the reef question, but you closed it before I could respond.
Okay. Is that Ethan?
Yeah.
Okay. I'll make a note of that and just Ethan Hewitt. Okay.
Thank you. Appreciate it.
You bet. Sorry about that.
Hi, I just wanted to check, is it going to be kind of the same thing where you're just like in the class Zoom during the test and we can come in if